As apparent from the slide, from the talk, we're both from Cisco. We're working at the Stockholm office, just a short walk away from here, so it's close. Cisco as such probably does not need too much of a presentation. Let's just say we're in the networking business. And the Stockholm office works mainly with network element configuration, both in the large and the small. So both configuration of single devices, but also configuration of whole networks or network service orchestration on a massive scale. So we're talking 30, 40,000 devices handled by a single program. And apart from that, it might be interesting to know that Cisco is sort of stealthily shipping some 2 million devices each year which has Erlang on them. That's kind of cool, really. So I'm here to talk about LUX. And LUX is a testing tool. It's not mainly used for testing Erlang programs. There's nothing specific in it for actually testing Erlang as such. It just happens to be written in Erlang, and of course the code we write is in Erlang, so we are definitely testing a lot of Erlang with it. The goal for it is system level testing, but it can be used for other testing at other levels as well. So it's not a strict system level testing tool, but that's mainly what we use it for. And a test script, now I'll show you an example of these. It's a sequence of input and expected output, and the expected output in general case can be a regular expression. And what's really cool, and we'll see that as well, is that it allows for scenarios, test scenarios, where we have a number of multiple concurrent sessions running. So we can do something in one shell, and see what happens in another. And that's, of course, a rather common scenario these days. And each session is a shell, and that's anything actually taking some kind of textual commands, because that is what a LUX script does. It does input with text, and then output something we can check for output match. So it's a good fit for system level tests and text-based interaction, where the output we want to match on is simple and can be checked with regular expressions. And it can be used for orchestration of concurrent sessions. So not just testing, but you can also do some other interesting stuff with LUX, where you control a number of sessions at the same time. It's not a good fit for testing graphical user interfaces, of course. Every tool has its limits. Structured output, if it's heavily structured, that can't be handled by a regular expression, is a bit difficult. If you only want to check the existence of some content, it's okay. But if you really want to parse the output, for example, XML, and get the internals of the structure, LUX as such is probably not for you, but you can still do it because you can plug in something that reads the output XML and then output something that LUX can handle. So we start with okay, the contrast was not good. So we start with a simple example. So we have a shell, a LUX script here on the left, and as you see, probably, so we start a server, we start a shell, which we called server, and then we send text to it. And what we do here is we just start an Erlang shell. We match on the output from Erlang when it starts up. We don't care about actual versions here, so we just say we want to see that we're starting up Erlang OTP. We want that it says something about an e-shell, and that it shows a prompt. And it actually says we want to see the first prompt number 1. And then we continue starting something and expecting to see a string output, and then we go on. And towards the end, we do a halt, and we verify that we're actually seeing the exit code. So we're doing a halt 3, and we're seeing that there's an exit code here. And that echo actually works, right, Hakan? And as noted, we can have, in the example, we see several matches on lines after each other. We can also send several inputs without matching in between. So it will just pipe input to the standard input of the shell being processed. And it's point to note is that the matching serves both as a verification of output, that is checking that the program is doing what we expect it to do, but it also serves as synchronization points. LUX will wait until it sees a match before proceeding. And this is how LUX views the world. Its input is a test script like the one shown before. And it will execute one line at a time, so it will feed, if it's exclamation mark, it's a bang, it will feed the input to the shell, and then a match expression, it will wait until it sees it and proceed when it does. And if there is no match found, it will fail. So the test script fails at the first non-match. And during this time, LUX will produce lots and lots of log files. When everything goes well, you don't care about them. When things go sour, you inspect the logs, and the truth is in there. There's a lot of logs. And again, the one shell view here is so again, feeding the script to LUX. LUX will feed the input through standard in to the shell and read, and it combines the standard out and standard error and looks for matches there. And a match is successful when the regexp is found somewhere in the output. So you don't need to match all the output, just some, saying, okay, here I want the prompt, and you don't care what came before the prompt. And future matching is then done from the point where the last match happened. And a matching fail, well, we say it's, well, if it doesn't fail, well, when do we know it doesn't fail? When do we know that it hasn't matched? Well, we wait, and we have a set timeout. So if it hasn't found a match within a certain amount of time, then we fail. So programs can be slow, so we might need to adjust timeouts, and that can certainly be done. Now let's go to a more interesting example. So classical client-server setup. And a chat server, it's dead simple, of course. So we have a server, we have a number of clients, and the server will produce, tell us of what it's doing in a log file. So you write the stuff, and then you test it, and you start with testing it manually, of course. So you start the server, it will produce some output, but not anything too much interesting. We saw the earlier example that it was matching on the starting server output. And then we start a client. And well, alone there's not too much to do, so we start another client. And the first client sees that the second client has joined. So we produce some input, and it shows up in the second terminal, and there's a appropriate reply, and we're done. So this is manual testing. Manual testing is boring, time-consuming, and will almost always fail. So let's put this in a LUX script instead. And here we now have multiple shells. We have a shell for the server, and we have one shell each for the clients. And LUX will create a new shell if it hasn't seen the shell name before. And if it has seen it before, it will just use the existing shell again and pipe input to it and then do matches. And then we just mimic the sequence of interactions we had in the manual session. Start the server, start the clients, send some input, wait for seeing that the second client joined, and then we send a ping. And the second client waits for seeing the ping and then responds with a pong. Right, cool. So we then feed this to LUX. And LUX will not be too happy about this, because it failed. And we were expecting a prompt, but didn't see it. Instead, in the shell, we got an error message. So it's the client is actually somewhat helpful here, asking, is the server really started? And of course, the problem is that when we do this manually, we're kind of slow. But when LUX does it, LUX isn't slow. But the server startup is slow. So the second client, the first client, will attempt to connect to the server before it actually has been fully started, and the connection will fail. So this is what we had before. And we replaced this with some proper synchronization, because we need to be sure that the server has started before we start the client. So we replace this with first some bookkeeping, where we actually delete any log that we might have. Because if we start to tail the log and there's previous content in it, of course we'll see the previous content and say, the server started. And then we start a separate shell which just tails the log and waits for a message in the log that the server has been started. And after that, we can go on to the first client shell, connect, and it's fine. And in the multiple shells view, it's just the expected extension of the single shell view. So instead, the script is now several shells, and LUX will create several shells, one for each shell in the script, and they will be created on demand. So they won't exist until they're actually seen in the script. And again, as usual, it will do piping input to standard in and the reading from standard out, standard R, doing matches. And again, the sync points, the matching will serve as sync points between the shells. And it will produce logs. And when you have multiple test cases, when you have multiple shells, it will produce more logs, because you'll see a log for or additional logs for each shell that you have in your test script. So, of course, this leads to You're doing test cases, manual, automate them, and run them, and they fail, and you adjust them, and you come up with new test cases. So you'll have a number of, after a while, you'll have a number of test cases in separate LUX scripts. And as a side note, one can actually name these LUX scripts something else than run.lux for those who might use LUX a lot, but we see a lot of run.lux files at the company. Wonder why. So after a while, you have a collection of related test cases, and these are, of course, collected in a test suite. And LUX can handle test suites as well, so it will run a number of test cases in sequence, and the sequence isn't really defined, is it, Hakan? If you don't... the names are sorted, so it's sort of defined. But the results are collected both for each test case, but also summaries for all the test cases collected together. That is the full test suite. And of course, you need to take care of normal test case hygiene, so test cases don't interact with each other. Start at a known state, do cleanups, etc. So there's no unfortunate interaction making test suites unstable. And there's some support for stuff like that, doing cleanups. And of course, test cases will fail. When they don't fail, we really don't care about the logs. You don't. So LUX is a fine producer of log files, and in most cases, we really don't have to care about them because everything is fine, it works, so we can just carry on. But when it fails, we want to know what happened, and the truth is in the log files. LUX will tell you on which line there was a match fail. There can also be warnings and errors as well. So a failure is when the test case fails to match. An error is when something bad has happened, like your LUX script wasn't correct or something like that. There's also so you'll see the line of the failure, but also with some kind of stack trace. That is additional line numbers if you got to the failure by a number of macro invocations. So I'm not going to look in too much into the logs, but we can see that in the default case, LUX will produce something like 12 logs in the simplest case. So you have you have one LUX script called simple.lux and a shell called server. So these are some of the logs presented for the produced for the actual test case. And I'd say the most commonly used, at least by me, is the standard out log, because the standard out log will show you every interaction that has happened in that shell. So you will see what has been input and what has been output. And you can see why it failed to match and what happened before, and see if there's something that happened before that you missed. Maybe there was an error happening that was output, and that's why you're not matching. And then you can also see the standard in of the corresponding shell. And then there are even more details looking at the event log, actually seeing what was sent in low-level detail, when it was sent, timers starting, timers expiring, etc. So there's a lot of information in the logs, and when things go wrong, this is where what you dive into. And then there's more logs as well. You get the configuration that was in place when the scripts were running. You get a copy of the test script because all these logs are copied to a separate directory for each run, which is also very convenient because that makes it simple to compare a number of runs and see what's failing, what's succeeding, if you're making progress with your test suite. And also very nice is the LUX summary. So there's a log as text and the same as an HTML, so we can open it. And there's also support for integration with other systems, so it can produce results in the test anything protocol format, which is very nice as well. So this is just the default number of log files that are produced. You can ask for more if you want them, if you need them. Matching then comes in a number of different flavors. The simplest case, or actually the most common case, is just using a single question mark. And there you have full regular expressions and expansion of variables. With two question marks, you don't have regular expressions, but variables are still expanded. So you might have saved something in a variable and you want to see an occurrence of that content again. And you can put that in a regular expression or the match expression, and it will be expanded. And then with three match operators, three question marks, you have a verbatim match. So everything as is, no expansion, no regular expressions. And there's also the possibility to do a multi-line match, also convenient. Since we have regular expressions, we also have the possibility to extract sub-expressions. So when we started the log, the server, it was nice enough to say where it was going to write its log file. So instead of hardwiring that into our test, we can, in the server shell, we can match on the trying to open log and then extract that value to a variable and then use that later when we want to tail the log. Nice abstraction, of course, and convenient. Most of our patterns are positive. Well, patterns are positive. We're saying this is what we want to see. And this is what we want to see to be able to proceed with our script. But of course, there might also be the converse case, where there are some things that we don't want to see. We might have a fail to match because something went wrong. We got an internal error, but didn't see it. So we can go back, patch our test case, and add what's called a failure pattern. So a failure pattern is local for a shell. And if it's seen, so this is how you write a failure pattern. So here we define a variable saying that we have a regular expression saying if it produces error. And our failure pattern is if we either see error or the shell prompt. So if it sees the failure pattern, it will fail immediately, saying this is serious, this is not something we wanted to see at all. And if we ran this and this wasn't present, we'd probably see an error. Oops. And as seen in some of the examples, anything preceded by a $sign is a variable or a variable expansion. And variables come in some different flavors. They can be local for a shell. They can be global, so they can be visible in all shells. We saw use of that previously, where we extracted the log file and bound it to a global name, so we could use it in another shell. And they can also be local for a macro. So this is convenient, nice abstraction. Less hardwiring, actually looking at the contents and using that again, or just actually setting a variable, binding a variable name at the start of the script, making it more useful. And also, as we saw in a previous example, if a numeric variable name $1, $2, etc., is a part of the last expression that matched, if there are indeed grouping expressions in there. LUX also has the support for macros, so that they're not expanded as a macro, so it's possibly an unfortunate name. Talk to Hakan about that, I have. So it's procedural abstraction. But the macro is run in the context of the invoking shell. So it's just a number of ordinary LUX commands grouped together, and you can invoke them. Oh, interesting. I never invoked the OK macro. So here we see a case of invoking the start client macro, which isn't there. And then we check for the prompt, something like that. And yeah, we had a local variable called me here. So we're sending that to the macro, etc. So for another shell, we could just bind me to something else or send it as an argument. So this is, of course, very convenient. The test scripts become shorter, high level of abstraction, and also very common to have a number of macros in common LUX include files to be reused between scripts. There's also additional convenience worth to be mentioned. There are loops, so we can iterate for over a sequence, a number of items. And in that there's a break pattern which you can supply, which is only used in loops. So you can end the iteration when the break pattern is seen. That can, for example, be used in a polling-like scenario where you're just trying to see if something has happened, and then you wait a bit and then try again. Timeouts, as said before, matching waits until it either sees the matching expression or a timer expires. And depending on what you're testing, you might want to adjust the timers. If you have them too high, your failing test cases will take a long time. And if you have them too low, your test case will be failing due to parts of the system not keeping up the test script. Also very convenient is there's a special cleanup shell. And this is always run regardless of whether the test case succeeds or fails. So it's used for, well, what the name says, it's cleanup. So in the cleanup shell, you'd typically terminate the other shells, terminate programs, possibly save logs if you want to do that. General hygiene. Checking general conditions on exit as well. Very convenient. So, some words about the implementation. And as seen from the presentation so far, there's nothing special in here that says, oh, we're going to test a system written in Erlang. It can be tested, can be used for testing everything, anything essentially, just that as it fulfills the input-output requirements, which we assume. But LUX is written in Erlang, almost entirely in Erlang. There are some small parts in C. And of course, looking at the use case, looking at what LUX does, Erlang is a very good fit. We have the concurrency, so because we want to control a number of concurrent shells. We have port programs, which make it very easy to start shells and send input and get output from them in a very convenient way. There's, of course, the built-in regular expressions, and as seen, LUX very heavily relies on matching. And again, and of course, timers in Erlang are simple. So, a minor look behind the scenes then of the implementation. So this is the single shell view. And the implementation looks like this, that we have a LUX interpreter which takes the input line by line. And when it sees a shell, it will create a shell process. So this is a man in the middle, so there's one process for each shell, and this is a process that will communicate with the shell. That shell process will start a port program, which will start a born shell. And it will connect with standard in and standard out. But there's also some additional magic done with a small C program called run pty, which acts as another man in the middle controlling the terminal, making the born shell believe it's interactive, and normalizes output, so it's simpler to do matching. And the part about making the shell believe it's interactive is actually quite important, because that means you can test CLI interactions. So you can test what happens when you type tab for completion, what alternatives do you get, etc. So that's very neat. And since Hakan is working with the CLIs at our department, it's no surprise that he has that feature implemented. And then, of course, there's a timer connected to the shell process controlling and the matching. So when it expires, the match fails. So in addition to looking at the logs when things fail, logs are always kind of static. They will give you the picture of what happened, but it's a static picture. So you might want to know what's happening during the process, during when you're actually running the test case. So there's a built-in debugger in LUX. So it has a possibility. For one thing, you can run with different levels of verbosity. The default mode is rather silent, but you can increase that and get a lot of output just while running it. But then you can also start a debugger, so an interactive debugger when you're running a test case, making it easy to put breakpoints at specified line numbers. You can single step. You can connect and interact with a shell. And you can view logs, etc. So here's a almost live debugging session. It was live before, but not anymore. So we start, sorry about the bad contrast. So we start a test case with and run LUX with -D, and it will start before line 1 and show where we are. And then we want to continue to line 15. We don't see line 15 here, but we possibly have it in a Emacs window or whatever. So we type C15 and continue. Get a lot of new output. And at this stage, we want to connect to this shell, to the server shell. And since the server shell is an Erlang shell, actually, we can start the debugger monitor, and we get a window popping up. And there we say, well, let's look at the code. New window pops up. And then we continue. And we just enter a simple, so right now we're in the server shell. So we don't want to be confused by any output in there. So we just type a single question mark to reset standard output. And then we can do a single step. And we saw that, we single step in the Erlang code as well. Okay, that's nice. We can view some logs. There we did the single step in the debugger. We can view logs. Can get help. And we can continue. And it's done. So that's very neat. So when you want to see what's actually happening during the test case, this is there for you. And then there's also a lot of infrastructure support. So we can add instruction for skipping test cases if we're running on a certain architecture. And at Cisco, the Stockholm office, we have software running on that is supposed to be running on different architectures and operating systems. So that's rather important for us. We can mark test cases as unstable, get output in various formats, and we can view, get a view of multiple test runs. So we can get a visualization. So that would look something like this. We're seeing that a lot of the test cases are green, so all the time. So they've been succeeding the full time. But some of them have been failing and then turned green. So this is a nice overview of things. Just some words of how we use it at the Stockholm office. So we have two products, one for configuration in the small ConfD and one for configuration in the large NSO. So we do a lot of testing of this. And we have running an automated test environment on Jenkins. And ConfD, since it's used for device configuration, needs to be run on different architectures, different operating systems. So that support comes in very handy. And well, I counted yesterday, and we have more than 4,000 test cases which are written in LUX. Some very small, some very large. So we're very heavily relying on LUX. But we're not using LUX exclusively. We're also using eUnit. It should say eUnit, not just unit. Common test, JUnit, some handwritten tests, legacy stuff, and etc. But we're not doing any scheduled manual testing at all before in conjunction with releases. So it's very automated, which is nice. LUX is open source. So find it there. There's a tutorial and a lot of the source code shown here and a lot more is present in the tutorial directory. And the chat server, if you need one, is there as well. And that was 40 minutes.
Interesting. I think we have time for 2 questions.
Hi. So my question is, So my question is, so there's only one global failure pattern, or
No.
can you have them like match after each match?
The fail pattern is local for each shell. So you can set a fail pattern for each shell, and you can change the fail pattern and reset it. So
I could express something like match this, and after this, I don't want to see this one.
Yeah. Yep.
A pattern that I was trying to debug very recently, and that would be interesting, would be servers behind the load balancer. So is there a way to expect output on any of more than one cells, or do you always need to specify where output comes out?
Well, I guess if you collect the output, that would be a way of doing it.
Anyone else?
Hi, I want to ask a question regarding the differences between TCL expect and the LUX. So with TCL expect, you can do logic within the script using TCL. Do we have like similar features with LUX?
No, not really. Or do we? Let's have Hakan answering this. I'm getting Hakan to talk.
Lucky you. As you saw in the slides where we started an Erlang shell, we can send any command to the Erlang shell and do logic in Erlang interactively. So we can start whatever system you would like to do. If you have the Bourne shell, you can run the Bourne shell logic in it, and then you can bind the output from that into variables and use it further in the script. So yeah.
Yeah, so you can do it by escaping, but not in the LUX language itself.
I think that's about what we have time for this presentation. So thank you very much, Cons and Hakan, and we will